Okay, so let's look at an example of an alloy. All right. The element is gold, so pure gold is just the element gold, yes? Pure gold is too soft for what? What do they like to make that's gold? Jewelry. Too soft for jewelry. Okay? And remember, because it's pure gold, it's all atoms of the same element, yes? Okay. Now then, gold is determined like 14K for 14 karat, 18 karat, and what is it, 24 karat? Okay, something like that. All right, so 14 karat gold is an alloy with silver and copper. $14K karat gold is 14 over 24, okay, which if you divided that out comes up to 58.3% gold. And the other percentages are divided between silver and copper. Okay, so that's an alloy. So they've mixed in silver and copper to give it some properties to make it more hard, yes, so it doesn't dent and scratch or break, okay? By and this is for all alloys, by properly choosing the proportions of each metal by properly choosing the proportions of each metal in the alloy, many desirable properties can be obtained. And they do this for all kinds of alloys that they make, that in order to attain certain properties that they want for any particular alloy that they're trying to use to better whatever it is they're making, strength, conductivity, anything that they need to better. So now we're going to change gears and we're going to go to suspensions. Okay, suspensions, heterogeneous. Heterogeneous what? Heterogeneous what? Thank you. definition. The solute particles are so large in the solvent that they settle out unless the mixture is constantly stirred or agitated. Example, jar of muddy water. Okay, as long as you keep shaking the jar, okay, everything will stay suspended in the water, right? Okay. The solvent particles are denser than the solvent water. And gravity pulls them to the bottom. Okay, so as long as you're agitating, okay, let's say this is the top of our water. Okay, everything stays suspended. In the water. As long as what? Yes. As long as it is stirred. Mm-hmm. Or agitated. Okay, and the color is going to be what color? Brown. Okay. When you leave it to sit, gravity takes over, and the heaviest particles will do what, kids? Settle to the bottom. So here you've got a column of dirt on the bottom with your water solution above. So this is your settled out dirt. And this is your water column. There. Now usually this water column will still be brown because it's going to have a lot of smaller particles that are going to stay suspended in the column, okay, because they're much finer particles, all right? But the heavier particles that gravity pulls down are right here. And a lot of times it takes more time for the very smaller particles to settle without being agitated. Okay, particles can be separated from the solvent by what? What did we use yesterday that couldn't be separated? By filter paper. So they'll get trapped in the filter paper. Okay? Particle size. Over 1,000 nanometers. Now again, all of these are determined on particle size. Over 1,000 nanometers. Okay, suspensions are the smallest. Solutions are the smallest particle size. Suspensions are the largest. Okay. And the third one may scatter light, but are not transparent. Okay. Now we're going to colloids, which is the intermediate size. So we've looked at solutions and we've looked at suspensions. Okay, this one is colloids. And it's also a heterogeneous mixture. Okay, so if we recap, solutions were what kind of mixture, kids? Those that were here yesterday. Homogeneous. Now then, colloids and suspensions are both what? Okay. Many colloids appear homogeneous. Because the individual particles cannot be seen. The particles are, however, large enough to scatter light. Definition of colloids. Particle size is intermediate between between solutions and suspensions? One nanometer. You remember solutions ended at 1 nanometer, yes? Okay, so colloids are 1 nanometer and suspensions started at 1,000 nanometers. Did they not? Okay, so colloids are 1 nanometer to 1,000 nanometers in size, in diameter. Okay, if we did a review of this, well, I'll do that after I finish colloids. The particles do not separate upon standing. Okay, so what makes this one like a solution? Those of you that were here, what makes this one like a solution?
They're mixed together.
They are mixed together. What did I just say? They do not what? Separate upon standing. That's like a solution, isn't it? Solutions don't separate upon standing, and neither do colloids. Okay? The particles do not separate upon standing. If you can't answer my questions from yesterday, what does that mean? You're not there yet. The particles do not separate upon standing. And cannot be separated by filtration. So both those properties are like solutions, aren't they? No. Wrong line. I looked at the wrong line. Cannot be separated by filtration. Okay. So it's a heterogeneous mixture, except it's still, the particles don't separate upon standing, and they cannot be separated by filtration. So that's like a solution. But yet it's a heterogeneous mixture, okay? Not a solution. How can we tell the difference? If we had two clear examples, one a solution and one a colloid, how can we tell the difference? Because they're going to look identical. Does that make sense? You can't see any particles. It just looks like you're looking at clear water. Does that make sense? All right, well, here's the difference. The Tyndall effect is used to identify a colloid from a solution. The particles excuse me, in a colloid will scatter light. Making the beam visible. Okay, so we're going to do a little drawing here. So we're going to look at a solution. Solutions do not scatter light. What'd I just say? Okay, so we've got a solution here, clear solution. We've got a flashlight over here, and the ray of light is coming across like yay. Okay? And basically, it does nothing. It may do some reflection off of the glass and stuff, but it doesn't show a good beam of light going through the solution. All right? So you may get some reflection. But no distinct beam through the solution. Okay? Okay, for our solution, let's say we use salt water. Okay? Now over here, for the colloid, and we're going to dissolve gelatin in water. So we'll just put gelatin solution, gelatin mixture. In water. Okay? Okay, so you've got a line, your fluid is up to here, yes. You've got a flashlight over here. And you've got a beam coming across. And what you will see is a very distinct line of the beam. Now you can also use a laser. This works really well. So I'm going to kind of color this for my beam. And my clear solution will be out here. Okay? So you have a very distinct beam of light. So a distinct beam of light cutting across through the solution. That is called the what effect? And who is the only ones that do this? Colloids. And this is how you can tell the difference between a colloid and a solution. An example, fog at night, when it's really foggy at night, you know it's hard to see through your headlights. But the interesting thing, so fog at night, you can see, if you were standing out to the side of your beam of headlights, say your beam of headlights are traveling this way, and you're standing back over here off the side looking towards the beam of the headlight. Does that make sense? Y'all with me? Okay. Fog at night, you can see the headlight beam from the side. So what does that tell you? That fog in your air is a what? Colloid. Okay? Fog at night, you can see the headlight beam from the side. Okay. Moving on up, electrolytes. Definition of electrolyte. A substance that dissolves in water that has dissolved ions. A substance that dissolves in water and has dissolved ions. What is an ion, kids? Going back to writing chemical formulas. Ionic compounds. What did you always have to assign? Ions have what? Positive and negative charges. Okay? Floating in the water. These charges, or these ions, okay, on the ions, conduct an electric current. Thank you. The positive and negative ions are free to move. Making it possible for an electric current to pass through the solution. To pass through the solution. Okay, everybody done signing change papers? Okay. All right, so example. Salt water. Okay? That means you've got Na plus and Cl minus separating and floating all around in your water. Yes? And so on and on and on, you have these ions. Everybody get the picture? Right? Floating all in your container. And they're all floating amongst the what? Amongst the water molecules. Okay? Now remember, we're on the atomic scale here. Everybody with me? So none of this you can see, but it's going on, right? So what you can see is the effects of it. A solution containing neutral molecules does not conduct electricity. Because it does not contain mobile charged particles. Mobile, charged particles. So that makes the difference, yes? So if you have a substance that doesn't form ions, it is a non-conductor. Does that make sense? Okay, so definition of non-electrolyte. A substance dissolved in water that will not conduct an electric current. I'm just going to put an E for electric, what? Current. Okay. Example, sugar is a non-electrolyte. Okay, so we're going to look at two light bulbs. Okay, one is going to be we're going to have two electrodes coming in a salt water solution. Okay, and the other one's going to be a sugar, strange S, solution. Okay. I could have just put water. Okay, so in the salt solution, we already looked at that the salt breaks up into Na plus and Cl minus. So this one will what electricity? Okay, so we're going to draw this light bulb here that has probes going down into a jar of salt water. Okay. You can see that they're not connected, and the only way the current goes from one electrode to the other is by the ions in the salt water. So this light is shining brightly. Okay? Alright, we're going to do it again over here. Draw your light bulb. Bring your electrodes down. Your container of sugar water. Okay? No light. And you do have an electrical source coming in here. You've got, so to speak, wires running into this apparatus here like so. So these lines are your wires. Okay. The sugar water does not complete the circuit. It's like an off and on switch. When the switch is on, you have light. When the switch is off, it breaks the circuit and there's no connection between the two and the light is off. Everybody understand? This is really a physics thing. You'll learn more about it next year. Okay? So the ions complete the circuit. Okay? And bridge the gap and allows the electricity to flow. Okay, here's your gap. Everybody see that gap? It's the ions that bridge the gap and allow the electricity to flow from one electrode up into the other. Okay? No ions is like an open switch with nothing to complete the circuit. And we're done.